and I am excited to introduce our next speaker, Ignat Korchagin, who is joining us from London, arrived in Armenia for the first time yesterday. He is an engineering manager at Cloudflare, and he will speak to us about how to protect yourself from the biggest internet threats. Please join me in welcoming Ignat Korchagin.
Thank you. Hello. Thank you for coming to my talk, and I'm very excited to be here. It's my first time in Armenia, first time at Jump, and the country is awesome, the people are so great. And today we're going to talk about the internet and how to protect yourself from the biggest internet threats. Does everyone hear me okay? Well? Okay, a little bit about myself. I am responsible for the Linux operating system in Cloudflare, which we run in production. I do like operating system infrastructure and infrastructure security and performance, and I enjoy low-level programming. So Linux, drivers, bootloaders, and other stuff written in scary, unsafe C language. So what are the attacks? So let's first talk about what kind of distributed attacks on the internet and why typical hardware boxes are not enough here. Let's start with a simple, non-distributed denial of service attack. Imagine you have a server, right? So you probably have some users accessing this server, and the server provides with your application, and all is good until some kind of an attacker comes. So what the attacker does, they start feeding junk traffic to your servers, overloading it, and basically making your users unhappy because your users cannot access this server. So what do you do in this case, right? Well, you usually employ some kind of a firewall. Usually it's a software firewall right on your server. You somehow block out the attacker, so your server is not overloaded anymore, and your users are happy again because they can't access the servers. So now let's zoom out a little bit and see how a distributed attack works. So all well and good, your service is operating as expected, but more attackers come. So they start again sending junk traffic to your server, again overloading it, and your users cannot access the server anymore. What do you do in this case? Well, you basically hide your server, your infrastructure from the internet, and you put it behind a bigger firewall. And at this point, it will be a dedicated firewall, either another machine, or you can even talk to some kind of vendor saying, do you have a specialized firewall solution? Again, all well and good, it kind of works until more attackers come in, and that bigger firewall becomes overloaded again. What do again? You buy even a bigger firewall. You go to your vendor, they say, yeah, we have this super cool new advanced firewall, which is probably much more expensive. You put it, it kind of works, but as more and more attackers come, your firewall will be overloaded eventually. And the problem with this approach is the attacker scales horizontally across the internet. But with hardware boxes, you kind of scale vertically, and you will always lose that race because scaling vertically is just usually more expensive, whereas scaling horizontally for the attacker is basically almost free cost. The way how these distributed attacks are implemented, so attackers find some vulnerable IoT devices, take control of them, and start attacking your service. So they basically get their compute capacity for free. Yeah, and when eventually you end up that your users cannot access the service and they're unhappy. Yeah, so the adversary scales the attack horizontally, but when you use hardware boxes, as I mentioned, you scale vertically. And because you will always lose that race, the number one thing you can take away from this presentation is if you want to efficiently protect yourself from global distributed attack, you need to have a global distributed defense. So how to build one, right? How to build a global distributed defense. Let's step back a little bit and try to understand how internet works. So the most basic type of addressing on internet is unicast. You all are used to it. You have a service which has an address. It runs on the specific hardware, and users via this IP address are getting routed to your service, and they do it well, right? Sometimes when you need more resources, you need to scale the compute capacity of your service, you use unicast with load balancing. So you have a device with an IP address, which we'll call a load balancer, but you put some servers behind that device, and it like distributes traffic. So you can scale your compute, but it's still unicast because it's a single point, one IP address in one location of the load balancer. Yeah, and users just always access this specific load balancer. But to build an internet scale distributed system, you need something different. And one of the technologies we use is called Anycast. So we have many servers across the world, and all these servers have the same IP address. So we can have servers in Armenia, we can have servers somewhere in Europe, in the United States, in Brazil, and they all share the same IP address. And the magic of the internet helps us then when users try to access the IP address, they get automatically routed via internet magic to their closest data center. And the nice thing about it is basically it works the same way for both users and the attackers. So when the attackers try to attack us, also their traffic is equally distributed across the servers across the world. So this is a Cloudflare global network today. So all these dots on the map is kind of like data centers or points of presence, as we call them. So imagine that when we have an attack, both our legitimate user traffic and attack traffic are distributed all over the world. So we don't have the single point of failure on the internet. And we are just using like the way how internet is supposed to work. We don't have any specialized security hardware for mitigating those attacks. It also allows us to have incremental cost, adding more capacity to handle more traffic. So we just add more points on the map, and we have more compute capacity, and we can handle more traffic. And it allows us to have this internet whilst horizontal scaling, and it does not only allow us to mitigate the biggest attacks out there, it also allows us to serve more users, so you can best of both worlds. Now let's talk about a different type of the attack called internet hijack. So what is the internet? Do you know, like when you type google.com, what happens? Internet is a big decentralized system. It's a network of networks, which we call autonomous systems. And each network has its own number, called autonomous system numbers, and their networks continue to exchange traffic between each other. But how do you know, like, if you're trying to access google.com, for example, how does the internet, this decentralized system, knows where to send your traffic, like which network is Google, right? So, and this is usually accomplished in the internet via BGP, Border Gateway Protocol. So the essence that each autonomous system, each autonomous network continuously shouts out to the network which IP addresses it serves. So if you, for example, want to access google.com, other networks will use these announcers to identify which autonomous system is serving that IP address and send the traffic back there. The problem that internet was designed a long time ago, and the Border Gateway Protocol as well was designed a long time ago, and back at the time nobody cared about security. It was kind of like a gentleman's agreement. If I own an IP address, I announce it. But if I don't own an IP address, I don't announce it to the internet. The problem in the modern world that sometimes now you can get these malicious entities on the internet which start announcing IP addresses which don't belong to them, and other networks will happily just start routing traffic there, causing a service disruption. So yeah, you see like these two IP addresses as the same, so part of the internet traffic will go to a malicious entity, and they can either just black hole it or cause a service disruptions or even pretend to be like an internet resource like google.com. So the way how to fix it in modern world, there is an update to the border gateway protocol where each autonomous system needs to properly sign their announcements. So, and by having the signature of the announcement, other networks can verify that the announcements are valid, and this way they can say like, okay, these two announcements are actually valid and they should act upon it, and thus they can just don't care about invalid announcement and disable such attacks on the internet. It also not only improves security of the internet, it also improves performance, because if you have invalid like sometimes invalid announcements happen not because of even the attacker. Sometimes the router in some network is misconfigured and it's causing a internet-wide disruption. But if you don't act on invalid announcement, like the overall end-to-end performance for users on the internet will be better. Unfortunately, since the internet is a global distributed system, to make it truly work, you need to cooperate. All the networks on the internet need to cooperate on this. So networks need not only to sign their own announcement, they also need to make sure they're accepting only only sign announcement from other networks. And basically not all networks on the internet do that. And for this, we kind of developed this website where you can go and check if your current ISP or your current network is actually implementing RPKI and is safe to browse. So on the right, you see the screenshot for my ISP, which doesn't implement the RPKI, but here you can see that this ISP implements it correctly. And basically, if you use that ISP, your internet experience is much more secure. So if you see that your ISP doesn't implement RPKI, reach out to them, say, hey, you actually need to do something. Okay, the other types of attacks we can see on the internet is CDN bypass. Who here owns a website? Oh. So if you own a website, at some point, or any other resource, you will probably want to use a CDN for either performance or even like security protection. And the way how it basically works is like, yeah, you basically put your resource behind a CDN, and what it does is basically you have the legitimate users accessing your resource through a CDN, and CDN will forward that legitimate traffic to your service if needed, if like the resource is not cached on the CDN. You also would have an attackers trying also to attack your resource, but the CDN should be robust enough and not to forward that bad traffic to your service, right? The problem with this approach is your service is still reachable via internet. It exists on the internet. It has a publicly routable IP address. So some attackers, if you accidentally, they learn your non-CDN, your public original IP address, they can just bypass the CDN. So they can just send the traffic not to the CDN, which is sometimes a big network and can absorb that attack. They can send the traffic directly to your service behind the CDN and thus cause a service disruption. What do you do in this case, right? Well, first of all, you have to if you're using a CDN, you have to really make sure to protect that your original IP address is not known to the internet. Sometimes it gets leaked, for example, if you don't want to send the old traffic through the CDN, for example, you have some kind of API, but that API, if you don't send the API traffic through the CDN, you will leak your original IP address and make this attack possible. But the ultimate protection from this type of attack, just make your service non-private. Don't make it internet routable, right? So no internet IP address, the attackers cannot reach you. but then how the users can reach your service. So in this case, many CDNs, including ours, allow you to establish a so-called egress tunnels. So even though your service is private, it can establish outgoing connections. So it establishes a persistent connection to the CDN. And when the users access your service, want to access your service through the CDN, their traffic is backrouted to your private service through these egress tunnels. If an attacker wants to access your service through the CDN, again, the CDN blocks it. But if the attacker wants to bypass the CDN, they can't, because your service basically doesn't have a publicly routable IP address, so they just can't easily send traffic directly to your service. Now, so at this point, we looked into how we distribute attack traffic on the internet scale, right? But you may have noticed that we only distribute attack traffic. We never filter it anywhere, right? So we try to build a system which can just absorb as much traffic. We shift the traffic around, but we never filter bad traffic. So let's actually zoom in what happens in the data center level for internet protection. So in a data center, again, you have a similar problem. You have your data center. It receives portion of the internet, legitimate user traffic, and the attack traffic. And the common approach to build data centers is, again, with a load balancer. So you have some kind of, so you want to scale your data center horizontally, right? So again, you have your load balancer with an IP address, and then it kind of shifts traffic for backend servers. But again, the problem with that approach that, where is the clicker? Oh, yeah, the problem with that approach is if you have too much attack traffic going to a single data center, your load balancer could still be overloaded, right? And then again, you may try to solve it with a hardware box. So you can go to some vendor and buy expensive dedicated load balancer, but again, you're falling into the trap of hardware boxes where you need vertical scaling, thus a lot of money to actually make it work. What you can do instead, you can use your own router. So if you build a data center, like most rack designs have a router called top-of-rack switch, right? So you already have a router in your data center. What you can do instead, you can remove the IP address from the router or the load balancer and put it on your servers, like the publicly routable internet IP address, and use a technology called ECMP to actually start announcing these IP addresses to your router. ECMP on a data center level works similar to BGP on internet level. So basically, your servers just announce which IP addresses do they have to the router, and the router will automatically distribute incoming traffic for all the servers which announce a specific IP address. So you have a load balancing, natural load balancing, without any kind of load balancer or even any specialized hardware equipment. It also makes horizontal scaling much easier. If you need more capacity, you just add servers, configure them. They, again, start announcing IP addresses to the router, and the router starts considering them when distributing traffic automatically. It's also easy to actually decommission a server for a maintenance or for whatever reason. You just turn it off, it stops announcing, doing ECMP announcement, and the router will not send any traffic there anymore. So no reconfiguration on the router actually needed, and you can really easily scale horizontally without any specialized equipment. So now we reviewed the data center level protection. So let's actually zoom in further down the stack what happens on the server layer. And again, if we go back to this picture, we didn't introduce any bad traffic filtering here again, right? So all we did is building an architecture which allows us to scale horizontally our capacity and shift traffic around and absorb more traffic. But no filtering is done yet. So now that we don't have any specialized hardware, we need to do the filtering on the server level, right? So anyone knows what this does? So imagine you have an attack, and in an extreme case, this firewall rule blocks all incoming traffic. Yeah, it's a really bad protection because you're blocking legitimate users, but let's design an extreme case. You want to block all incoming traffic. Is that good enough to mitigate an attack? What do you think? It's okay? No, it's not okay. Actually, if you even block all incoming traffic on your server, it can still be overloaded, and we proved it in Cloudflare. And the problem with this is how servers and operating system worked, and firewalls in the operating system work. So again, let's zoom in into the server. The server receives legitimate traffic and the attack traffic. So how does servers actually process incoming packets? So you have a network card which receives a packet. It issues a hardware interrupt and passes the packet to the operating system in the driver. What the driver does, it allocates some memory. In Linux, it's called SKB. It copies the packet from the NIC, re-enables interrupts, and passes it to the next layer. The next layer is data link layer. So at layer 2, it passes the data here, and the data link layer does some other stuff. So it processes layer 2 headers like the MAC addresses. It calculates a checksum. It can merge some kind of like adjunctant frames for performance, et cetera, et cetera. Then it passes that data to network layer in the operating system, layer 3. And again, what it does, it parses the IP addresses, the layer 3 headers. It can do some GREO. It can implement connection tracking. It calculates layer 3 checksum, considers routing, and only then it will reach to your firewall rule, which says, hey, just drop that packet. So if you receive bad traffic, even if you have a block everything firewall rule, your operating system has to do all that to basically, and it still does a lot of processing. So you have a very volumetric attack. It can still overload your server because it has to do all this thing. Yeah, and we proved it in Cloudflare, so if we attack a Linux box with enough traffic, even if we drop all file system, we see CPU spikes, and the servers become unresponsive. So in Cloudflare, we enabled and used, and we actually were pushers of that technology in the Linux kernel called Express Data Path. So the operating system, Linux, allows you to inject small eBPF programs, programmable filters, early in the packet receive path. And the advantage of this technology, it's very fast, it's programmable, so you can program almost arbitrarily filters to really fine-tune your firewall. It's actually safe, even though you're reprogramming the in-kernel firewall, BPF was designed to be really safe, and it will never crash your server. And yeah, there is some documentation about it. So what it essentially does, it allows us to create these small filters. And in worst case, we insert the filter in the driver layer, which can filter packets right after the driver receives an interrupt from the NIC of a new packet arriving. And in more advanced case, if you have a cooperating network card, you can even have these filters installed directly on the NIC itself. So your server will not even receive an interrupt packet if the packet was filtered originally. And it also allows you to handle really large amounts of bad traffic because we filter it at the source immediately, and we protect our servers from doing all this unnecessary work to drop malicious traffic. The another advantage of XDP and eBPF, it's really programmable. So you have a very rather complicated programming language to create fine-tuned filters. So how do we design these filters? So Again, this is the Cloudflare network. All of these data centers, all of our data centers, send sample traffic to a centralized location where it's being continuously processed and analyzed for malicious behavior. And that centralized location kind of writes these eBPF programs for us automatically and distributes them back to the data centers to actually block malicious traffic. We also have a data center local version of the same software for shorter feedback access. So, for example, if one of our data centers gets attacked by a novel attack, so that localized version will actually learn automatically how to mitigate that attack and use and generate these eBPF programs, these filters, to block it very efficiently. But not only that, it will communicate back its learnings with a centralized system to other data centers. So when we encounter the same type of attack in other data centers, they're kind of automatically protected already because they know how to mitigate that traffic. Is there any Star Trek fans here? Oh, yeah. So who knows Star Trek? I like to envision Cloudflare network and this system as Borg species, because kind of if one of Borg learns how to mitigate a certain type of blaster, all of Borg learn it eventually. So this is I like to envision Cloudflare as a Borg network. Okay, so now we reviewed the internet-wide threats. We reviewed the data center-wide protections. We also dive deep into the low-level server internals. But what about application-level protection? It's funny, to make this screenshot, I didn't have to search for the internet. I just went to my spam folder yesterday and took it. And voila, I always have emails, something like that. I want an M1. Wow. If I open this email, I mean, Google tells me that it's likely a spam, and it has a PowerPoint attachment, so should I open it, right? It probably has some kind of... So what is the problem here, right? If you click on a bad link in your email, so let's say you have a computer, and usually you run some programs there, so browser sessions or other software. If you click on a bad link, bad things may happen. So the least best thing which may happen is your current browser session might be compromised. So the attacker can do bad stuff in your browser session. In a worse scenario, so it can also compromise the adjunctant programs or browser session, steal your credentials, etc., etc. And in the worst case, if you don't patch your operating system often, even the whole machines can be compromised. But people are people. They will usually, once in a while, you will always click a bad link. So how do you protect from that? Well, one of the solutions would be to implement a browser isolation. So you have a browser, you can put it in a sandbox, and you kind of hope that the sandbox will provide enough protection for if you click on a malicious link. But that is not always the case, because sandbox techniques are not ideal, and it's a continuously race between the attackers and the sandbox designers. Attackers come up with new ways how to escape the sandbox, and the defenders then need to understand how to implement better sandboxes. In order to efficiently mitigate this attack, just don't run the browser on your computer, right? If it's not local, it can't hurt you. So one way you could do that, you can actually either use your CDN or other cloud provider, which may provide a feature called browser isolation. So instead of running your browser locally, it allows you to run your browser in a remote isolated session remotely. And if you accidentally click on a bad link, yes, some of the session might be compromised, but the attacker cannot run away or from that session. And usually these sessions are quite ephemeral in one time. So as soon as you finish browsing that malicious website, that session, the whole session and all the resources and compromised stuff with it gets into the junk folder. I think that's all I wanted to cover for you today. I hope it was exciting. And some conclusions are, which you can take away from this talk, is to protect yourself from global distributed attacks, you need global distributed defense. If you're thinking if you're thinking about an architecture and you notice you're protecting from attacks by scaling vertically, most likely you will always fail because you will eventually lose the race against attacker in growing the compute capacity. The network is the computer now, actually, and the internet is a security perimeter. With the COVID, all the remote work, we cannot say anymore that our service is some kind of behind castle and moat, data center, private networking or something. Your services are in the cloud, on-premise, and hybrid. They're distributed across all over the world. Your users are distributed the world. Your employees are distributed all over the world. So you can't only just rely on simple networking, firewalling, and separation to actually make your resources secure. And finally, practice defense in depth. So because of the natural distributed nature of the systems we build today, you definitely need to consider the security on all layers, your infrastructure and the software stack as well. Thank you very much, and I'm happy to take questions.
Thank you so much for sharing, Ignat. And let's get the QR code up on screen for any questions you may have for Ignat. QR code coming. And again, I'll give you guys 1 minute as the questions come in, so please go ahead.
I can see the coffee break coming up.
Yes, you are our last speaker before the first break. And ladies and gentlemen, we'll have our coffee break until 12:05, and then at 12:05 we can gather here again for the following speaker. All right, Ignat, you're ready for some questions? No? Maybe, maybe not. Let's see. All right, so question number 1. How do you route the same user to the same server using the same IP on different servers? Because in LAN, this causes problems.
Can you repeat that because of the
Yeah,
echo?
of course. How do you route, oops, my apologies. How do you route the same user to the same server using the same IP on different servers?
I imagine the question is related to Anycast versus CMP. So the first layer of Anycast, and then when it goes into data center, it becomes in CMP. And yes, indeed, we need to make sure that if we're processing a TCP traffic, that traffic ends up on the same server. So we have several technologies for that. Well, first, we do reuse what internet allows you to. So the way how BGP works, this traffic from the same user will always be routed to the closest data center. So it will end up in the same data center eventually, unless we put it offline. In the data center, the CMP is used technology called consistent hashing. So basically, the router, when it decides to which server it needs to forward the packet, it uses a combinations of L3 and L4 headers. And by that, it calculates a checksum, and then it basically creates an index of the server where it needs to send the traffic. So eventually, the traffic with the IP packets with the same layer 3 and layer 4 headers will always end up on the same server, again, unless we put it out of production. We also have a technology called Unimog. So, for example, if we do need to take out of the server, if we just turn it off, actually it will disrupt some of the connections. So we have this technology which we can drain the server. So we can start routing new connections while the server is still on the line to nearby servers when we enable that technology to drain the server, and we wait for a bit till the existing connections will gradually fall behind. And then that the new users will use a different server as the current server is. I hope that answers the question.
Thank you so much, Ignat. Next question with the most upvotes so far, so the most popular. The question is, in case we use egress tunnel but need a static IP address which will be whitelisted in third-party systems to access their APIs, what can we do? Do you want to read the question?
Yes.
In case we use egress tunnel but need a static IP address which will be whitelisted in third-party.
Technically, you can do that. So if you want, most of the CDNs will allow you to have a dedicated static IP address, but still manage it for you on the CDN level, so you can still use egress tunnels. I personally advise that because of the conclusions I just said you. Like, whitelisting and allow listing an IP address is kind of like an old school approach of like you have this secure network perimeter, and it's usually like it's asking for trouble. Like at some point you will migrate from one CDN to another, from one cloud to another, and that IP might change, and then you will have disruption for the user. So this technique is very fragile, or you then accidentally add another instance of your servers with another IP address, and you will forget to update your whitelisting, right? So try to employ a different solution here. For example, if you have users connecting to the APIs, use mutual authenticated TLS, right? So you can basically trust the connecting entities. They have access to the API without relying on where they come from. Does that make sense?
Thank you so much. Next question, a little simpler. Has the Cloudflare network ever been hacked thus far?
The unofficial answer is no. The official answer is, to the best of our knowledge, no. Although we did have outages due to misconfiguration, so, but I don't think we had security incidents at that point. We did have, not on the network side, but on the email side, we see like very sophisticated targeted email phishing, and we also use some of our products to protect ourselves, as well as just the general security training to, and one of the products I actually showed you, it's remote browser isolation. So users click on links and they will probably, hopefully will get a remote secure browsers and they will not be hacked. Also, plus some security training for employees to be more vigilant.
Thank you for the answer. All right, next question with the most upvotes. Is it possible to have a fully secure application, the data of which, ooh, it just moved. Is it possible to have a fully secure application, the data of which will be stored only in encrypted ways, and no one, even the application owner, can access it except the data owner? Fully secure application is some kind of utopia, right? So if we can, if you can build a foolproof security system, you probably don't need all of that, which I described earlier. But yeah, you can always be as close as possible. Yes, you can have data locality in clouds, and including Cloudflare. You can employ some cryptographic techniques. You can have combination of different network application layer and server layer security controls to ensure only like authorized entities can access the data. But again, in general, in security, it's a continuous race between like people who build these systems and the attackers who can find novel ways of accessing this data. And you know, like statistics show that specifically for data leaks, it's usually these days cheaper to buy a person who will, an insider who will leak the data instead of just like trying to overcome these security defenses. So, and this is how it usually happens in the first place. Thank you for the answer. Ignat, you're very popular today. There are a lot of questions still coming in. We won't be able to address all of them, but we'll get to a few more. And please find Ignat during the break if your question doesn't get addressed.
Catch me. I said, if you need more questions, catch me later. I speak English, Ukrainian, and Russian, so we'll be happy to answer all of them.
I think we'll just take two more since we have the time.
Okay.
Next question. What is the most famous tool to use for your product to identify malicious attacks?
They read because of the... Oh.
Most famous tool to use for your product.
The most famous tool in our product to identify malicious attacks. We used to have a system, and we blogged about it on the public blog post called GateBot. So it was kind of very popular, but it was the early incarnation of our system. Now, the thing I showed you here in the slides, this is like the second incarnation of the same system. We call it internally DOS-D. And it's a combination of like some heuristics as well as some machine learning to actually identify the malicious traffic. But I don't think it's a dedicated tool. It's like a combination of many systems which cooperate to actually like pinpoint a specific malicious.
Thank you so much. Next question, how does Cloudflare CAPTCHA work? If you could briefly explain. It seems so much better than Google's, question mark.
How does Cloudflare CAPTCHA work? To be honest, I don't know. Because I'm mostly working on the server here, and this CAPTCHA is a little bit of like a black box and magic to me. But I'm really, really happy to learn that it's better than Google's. And actually, internally, we're kind of against CAPTCHAs, so we continuously try to innovate and find other ways how can we make internet safer for users and like not make users actually even make CAPTCHAs. I think one of the attempts we made was called blinded tokens, where we had a very deep research and a combination of some cryptographic techniques which allowed legitimate users to obtain a bunch of tickets and then use them to access resources instead of solving CAPTCHAs. And like we proved that it kind of really, really improved the user experience because like we waste a lot of time solving CAPTCHAs on the internet, unfortunately. And I think someone published an article recently that AI is actually now better at solving CAPTCHAs than users, so why do we have CAPTCHAs in the first place?
Okay, well that perfectly segues into one last question. Do you use machine learning and AI to detect popular ways of attacks and prevent similar ones?
Yes, we use machine learning. We have even a product for that called bot mitigation, which is quite effective. So not only bot mitigation, it's called bot management. So you can use some kind of combinations to protect your web resources from bad bots, which like scrapes data, but you can also allow good bots from search engines, etc. So yeah, and it's based on machine learning, as well as we use machine learning internally to actually identify some types of attacks. And yeah, and recently we also announced we'll probably be opening some of our capabilities at some point to the public, so like users and customers can also use Cloudflare to run like inference model directly on the edge closer to your users, which I'm really looking forward to how it will work.
Thank you so much, Ignat. Please join me in thanking Ignat for his time and expertise.
Thank you.
And feel free to find him during the coffee break. I know many of the questions went unaddressed, but we do the best we can.